welcome everyone. Unfortunately, Vivian is unable to attend today. She is traveling, but she said to pass on a hello. If you're joining for the very first time, this is the monthly seminar series at the SMART Network at the University of Alberta. And for those of you who also may not know, SMART stands for Sensory Motor Adaptive Rehabilitation Technology. The SMART Network has more than 300 researchers, support staff, and trainees from different disciplines that have all come together to develop interventions to improve the quality of care and health outcomes, particularly for persons with neurological conditions. Without further ado, I would like to introduce our speaker today, Dr. Patrick Pilarski. He is a Canada CIFAR AI Chair and Principal Investigator with the Alberta Machine Intelligence Institute and the Reinforcement Learning and Artificial Intelligence Laboratory. Dr. Pilarski's research interests include reinforcement learning, real-time machine learning, human-machine interaction, rehabilitation technology, and assistive robotics. Within the SMART Network's Blink Lab, he leads an interdisciplinary initiative focused on creating intelligent artificial limbs to restore and extend abilities for people with amputations. And with that, I will pass it over to Dr. Pilarski.
Thank you, Michelle. I'm gonna try and find my screen here. There we go. All right, perfect. So it's always awkward hearing someone introduce you. So thank you, folks. I'm excited to be here today. Can you all hear me? Laura, maybe a thumbs up, or Michelle, thumbs up. So, okay, good. I can see some of your faces on video, so I can actually see check-ins. Thank you, everyone. Perfect. So I'm excited to be here. It really feels like we are moving out of our time hiding in our basements or in our caves and rolling out back into the world and sharing what we've learned after reflecting for 2 years. So this talk really is, I think, something that sums up a lot of the thinking that we've done over the last 2 to 3 years. And I'm going to be sharing today mostly work that I will contextualize based on my role at the university in the Blink Lab and the SMART Network. But I do want to say it's involving a lot of work from a lot of people at a lot of organizations. Some of them you can see here. I'll be sharing work especially from U of A and some of our DeepMind team, but it involves collaborators from all around the world. So I'm excited to bring you this viewpoint today. The usual conflict of interest disclosure is that, yes, I don't have any relevant conflicts to disclose, but I do want to note again, I'm employed by DeepMind and I'm on the board of directors of the Alberta Machine Intelligence Institute. So I'll start with this. Hopefully, can you all see a toe? You can see a toe. Yeah, okay, someone said yes. That's great. Okay, thank you. So cool, we can see a toe. I want to start with this. This is an example of the Cairo toe. This is from somewhere around 950 to 700 BC and is one of the earliest dated known uses of a prosthetic technology. There's an excellent article in The Lancet I encourage you to read if you want to learn a little more, and a great article in The Atlantic. But I'm using this as an example of how that we have, as a species, use tools to extend ourselves for literally thousands of years. And it's not just us. If you're really excited about how animals use tools to extend or enhance their abilities, you can look at a great book by Frans de Waal from 2016. But this is the point I want to make, that we have for a very long time used tools to extend or augment ourselves. And that over that time, our tools have adapted and changed in epochs and iterations. And similarly, we've adapted and changed to our tools. And where I want to go with this talk and towards one of my first points is that we are at an inflection point now. I mean, we can look back at what might, if you think about falconers, a socio-technical gyre that has gone back for thousands of years of us interacting and changing alongside our technology. But we are at an inflection point, and that inflection point is that we are now able to craft tools that are different than they were before. We can craft tools that will now not just work with us, but will actually change and adapt to us as we use them. And in particular, and of note to the talk that I'm giving today, that we are actually able to imbue our tools with some of the hallmarks of intelligence. This is really transformative and changes the way that we interact with our assistive technologies, the devices that support us in our daily life. So I'll show a quick video now. Hopefully the video will start playing. These are just a few of the devices that we have at the Blink Lab on campus and in the SMART Network. We can see that the tools have changed. This is very different than the Cairo toe that I showed you on that last slide. We have seen an unprecedented change in terms of the sensing technology available to us. Step changes in actuation, in battery power, and especially, and this is where I think we've seen a very noticeable step change or ramp, is in the computing technology available to us. We've seen a huge change, a huge delta in the advanced computing technologies, especially machine intelligence, that we can deploy on devices. And in particular, we also have a large change in how the hardware supports machine learning technology. We now have chips that are especially dedicated to supporting advanced computing. So I want to use those as an example. Like those are, it's great. We've seen a lot of change. I'm going to zoom out a bit now and show you all the cool new slides I built. I said it was a brand new talk, but I will zoom out a little bit and think about how humans interact with the world around them. And usually we can break this interaction down into perception, action, and cognition. A person's ability to use their sensory motor apparatus to perceive the world around them, to take actions upon that world or affect change in that world, and to perform acts of cognition, the thinky bits, as we say. So when we get farther along, we can see that just interacting even differently. Some of you may remember, if you've seen me give talks for years now, you remember I used to start my talks off with a picture of a stick. And I was like, why, you're going to talk in AI, why are you showing me a picture of a stick? But here I'm going to show a different view of that, where we now have someone that is very specifically or tightly interacting with a piece of technology. This technology is coupled to them. And if we sort of think about the words of thinkers like Engelbart, this is an act of extension. Is a way of extending and modifying the means by which a person might sense or perceive their world and might act upon that world. It adds information channels to that person and also adds their ability to up their skills to, in fact, change how they grow and interact with that piece of technology. There's some really cool work surveyed here. I'm citing Serino in 2019 on how we can actually think about this as the parapersonal space of a person, and how in fact our cortical representations extend out to encompass and incorporate those tools and the channels of information available by way of those tools. But we go farther. This is something I think many of us know and love. You can see this here. I have extended this diagram to show you holding your cell phone and all of those channels of information that flow between your face and your cell phone as you walk across the street holding your phone, or instead of paying attention to your colleagues or quickly texting someone. I think we can see that our newer technologies, especially those that involve computing technologies, perform an act of amplification. And I'll just go back. Many of you who know me know that I love to draw upon the work of William Ross Ashby. And so I'm going to cite the Introduction to Cybernetics from 1956 and say that Ashby says that really amplifying the ability to select or choose between one of many options amplifies the intellect. This selection builds upon a framework of two systems with a communication channel open between them. And so I want to just think about this, is that when you're holding your phone, you have many communication channels that are open between you and that device and the world around you. But I think it goes farther than this. And I just want to show you this sort of very dramatic slide to say that it's not just us interacting with a single piece of technology. And if you think this slide perhaps futuristic, I would like you to think of it as a superposition of things that are happening right now. We see that people are in fact engaging with technologies like their cell phones, they're wearing their Fitbits, people have pacemakers, people do have spinal stimulators or recording devices. They have devices that might be monitoring and preventing pressure ulcers by stimulating your skin and muscles. There are cochlear implants, deep brain stimulators. People are using neuroprosthetic technologies in their daily life. We're starting to see a system wherein we can imagine people interacting with a diversity of systems, all with channels flowing and open between them. And so I like to quote JCR Licklider when I bring up a topic like this, because Licklider said in an article in 1960 that the hope is in not too many years, and this again was 1960, that human brains and computing machines will be coupled together very tightly, and that the resulting partnership will think as no human brain has ever thought and process data in a way not approached by the information handling machines we know today. And so I want us to think about this and to think about these tightly coupled interactions and how they might in fact be very crucial for how we move forward as a society, as a species. My soapbox, of course, you'll hear this over us talk, is that these tightly coupled interactions should be coupled and continually adapting and improving interactions. And that is important, not just for neuroprostheses as the title of this talk, but for assistive technologies and devices that support us in our daily life writ large. All right. Awesome. So I'm going to zoom in a little bit now. Hopefully everyone remotely is now seeing a picture of a prosthetic limb. This in fact is the transradial socket and the handy hand developed in our Blink lab, the socket by Hallworth and colleagues, and of course the handy hand by Dylan Brenius, who I can actually see over there in the back. Wave, Dylan. No one else can see him, but I swear he's waving. This is usually when we think about humans' interactions with their assistive technologies, we think very largely about the control pathway. What do I mean by this? I mean the pathway by which we sample signals or information from the human body relating to that human's intent. For neuroprostheses, upper limb especially prostheses, as I'll focus on for this talk, this is really the human's motor intent, how they hope to move or use their arm to interact with the world around them. And my screen went black. Did your screens go black? No? No? Okay, perfect. Well, then I think we're all on track, but I just lost some of my data streams here in the room. So I apologize if any of you are all seeing this, but let's just note this for our space. This is spectacular. Okay, is everyone still seeing my slides? I really hope that's true. Okay, thank you very much for nodding. Okay, so the control pathway. In the control pathway, we can think about the mapping of intent or human motor control to the motions of a robotic device, say the way that a hand might open or close, or the way that a wrist of a system might rotate. This is if we look back even to the 1960s, there's been intensive effort devoted to how machine learning technologies or machine intelligence might be used to broker those relationships in the control pathway, how the signals flowing from the human body might in fact be mapped to the many different modes or functions of a device that's supporting their life. For an upper limb prosthesis, you can think of this as mapping, say, the signals from the muscles of the human body directly to the different grasping patterns or the opening and closing and rotation of the wrists of a prosthetic device. One way to think about this is that there's a diverse set of signals and information flowing from the human body and a diverse set of signals that might be entered into that assistive or robotic device. And that in fact, the learning machine's job is to change or alter its internal structure so it can facilitate that mapping in a smooth and natural way. If you want a review of how this works, we have a very nice review in IEEE Signal Processing magazine led by Amin Shahada, which actually surveys the state of the art in machine learning in the control pathway. So the topic of this talk, I really hope that to talk about feedback, you saw my fairly bland, but I hope at least informative title about the emerging role of feedback in neuroprostheses, machine learned feedback. So I want to switch to the feedback path. And so here the feedback path really is the way that information signals or environmental context flows from a neuroprosthetic device like an upper limb prosthesis back to the person using it. And traditionally, like you saw right away in the control pathway, I showed you something wherein there were a bunch of wires that were sort of moving from the arm to the device. In the feedback pathway, that's simply not the case, especially in upper limb prostheses. Often the feedback pathway will be non-existent in terms of the actual technical innovation. It will be something that is brokered by a person actually visually attending to their artificial limb as they use it. A person that can hear the sound of the motors moving in the elbow or the wrist of their device, or the mechanical forces that are transmitted from that device to them via the socketing or harnessing technology as they interact with the world around them. So the feedback path, comparatively speaking to the control path, is something that has been much less explored. There are great examples, though, of engineered feedback, and there's an excellent review by Schofield et al. Recently that painted all the different ways that we might start to think about synthesizing the information from an assistive device like a neuroprosthesis and putting that back in contact with the human body such that they can use that to make informed decisions about how they're engaging with the environment around them. And so there are ways of doing this. They've recently been enhanced as well by some really quite transformative surgical innovations. And so one, actually as a subject of expertise here at the University of Alberta, we have targeted sensory innovation. Jacqueline Hebert and colleagues have really pioneered some amazing ways of mapping signals from a prosthetic limb back to a rewired part of the human nervous system such that a person might be able to actually feel as if it was on their own finger when their robotic finger is touching an object, or feel the sensation of someone stroking the back of their hand by way of some reinnervation surgeries. There's also work by Marasco and colleagues and others from here at the University of Alberta and other sites looking at how to communicate the sense of kinesthesia or proprioception, the feeling your limb is moving through space and where that limb is in space. But I will say that this is, and maybe this is one of the very first points of my talk, and the thing I hope you, if you take away maybe three things, I've come to maybe the first takeaway of the talk, which is that while I showed you the machine learned path in the control pathway, whereby machine intelligence, machine learning brokers, the control channels flowing from a person to a machine learned feedback in these contexts is relatively underexplored. I would say unexplored, but that's not strictly true. My graduate student, Adam Parker, and I have looked at and surveyed some of the ways that it has been used, but it is very, very sparse, comparatively speaking, despite the promise to be able to synthesize a vast amount of information in the world and communicate it back to a person. So if you want to check out for the first part of the talk and take one thing away from it, it's that just know that this area is underexplored. There's a large open space in our understanding as to how we might use adaptive systems like machine intelligence to broker the feedback relationship between an assistive technology and the person using it, especially in upper limb neuroprostheses. Okay, take a break for one sip of water and watch the screens behind me flicker with static. Okay, so let's now move on from that particular line of thought to what actually is the gap. If we truly wish to embrace some amount of adaptive or learned feedback from a device to a person, I'm going to argue that there is in fact a scientific gap that we have to cross. There's a gap, and we've argued this in some of our recent work on one of the topics of this talk today, that the gap is between these expert designed or fixed signaling systems, some of the really impressive and still very powerful technologies that I showed you and alluded to in the previous slides, and what might be considered truly emergent or fully learned signaling between a machine and a person, or back and forth between a person and machine. This is a scientific gap. And I think we have good evidence that crossing that gap might be a good idea, in terms of the flexibility, the adaptability, the effectiveness, and the reduction of human design time that might be present if we were to be able to actually think about learning in that feedback channel. I think folks like Crandall in their article, Cooperating with Machines, made some very compelling points as to why this might be powerful, as have some very other good reviews, and especially some of the empirical work by Natasha Jacques and colleagues. I think there's some really good evidence that in fact we should be trying to cross this gap. So today I'm going to show you not how to cross the gap. I'm not going to be like, oh yeah, cool, this is what I thought about for the last 2 years, you all win. We figured out how to like totally jump that. As anyone who works with me know, I like to think about communicating science and doing science in terms of like very much like stepping stones across a river in a Japanese pond, where you have to take natural steps, and those steps should all be comfortable and you should be able to feel secure in each of those steps. So I'm going to present to you today a first natural stepping stone. And this is work that I'm going to start out with some work that has largely come out of our team here at the DeepMind office for the last 2 years. And that's the idea of Pavlovian signaling. This was in the abstract, and so I'm going to help walk you through it today. But I'll bring this definition from 2 papers that we just had presented at the Adaptive Learning Agents workshop at AMOS, but also a larger tech report that we released. But the idea today is I do want to talk about Pavlovian signaling. And I know I'm talking to some people in the room here who know a lot about, in the physical room, who know a lot about it, but maybe you'll see why I am so excited about Pavlovian signaling and think it is actually this important stepping stone across that gap towards fully emergent communication. Here we define Pavlovian signaling. I'll give you the definitions first, is that Pavlovian signaling is a process wherein learned temporally extended predictions, by this I mean predictions about some window or horizon into the future, are mapped in a defined way to signals that are intended for receipt by a decision-making agent. So we have learned predictions about some window over to the future that are now being mapped to signals with the intent that those signals will be received by some other agent that is going to make decisions, take actions in the world based on that information. And as maybe a subtle point, it's important that these signals are in fact grounded for the sender, for the agent that's sending them, in the definition of the question, the definition of that predictive forecast that they're making, and the mapping approach that generated them. If you want to think about like this, we can go back to Pavlov in 1927 and start thinking about trace conditioning, to think about the interval between two forms of stimulus. And we might start to think about this as a temporally extended prediction about the onset or about some qualities of a stimulus that will be approaching in time. And so if you want to think about this very simply, this is an accumulation style prediction, where the accumulation rises in the event, in the onset of a future event. You might think that the thing that is emitted, the signal that is emitted, is in fact, let's say, a value of 0. Well, that prediction is below some fixed threshold. The minute that signal crosses a threshold, it flips over to be a signal that is a value of 1. And that signal is emitted to another decision-making agent. This should sound pretty straightforward. I hope this sounds really straightforward, because it is. But that's what makes it powerful, understandable, and we can leverage it to do some fairly exciting things. So now let's imagine this interaction. I'm going to switch over to a video, and you can listen to someone else talking for a second soon, I hope. But that you can imagine now that we have a dyad that we have created. We have a person. In this case, let's imagine a person in VR, because that will be apropos to our next example. Person in virtual reality who is interacting with an environment and has to make decisions based on some event that occurs in that environment that might be hard for them to perceive. They might not be able to fully observe that particular event. Now imagine a second agent, here we're calling it a co-agent, which is able to also observe that event when it occurs or partially observe that event, and can now start to build up forecasts about that event. When that forecast exceeds some threshold, the agent will be able to emit a signal to the person who's making decisions. We have a human agent and a co-agent, a Pavlovian signaling co-agent, which is helping to build up expectations of an event of interest and communicate that to the person so they can make good decisions. Okay, I'm gonna switch over and I hope this works. You're going to hear the words of Dylan Brenius now. So we actually have a video from the ALA workshop that just occurred. And so I'm going to let this video play and you can listen to Dylan for a second, explain that work, and then I'll move on to the later bit. So give me a thumbs, someone give me a thumbs up as well if you can hear the audio when it.
As our technology has evolved over millennia, so have our interactions with it. Technology has traditionally been hand-engineered to produce reliable performance and in turn, predictable human interaction. Even where modern learning systems have been employed, the system is typically pre-trained before deployment, when its parameters are frozen and its behavior is fixed. Technology that dynamically and continually learns while it is being used has great potential, but comparatively little research has investigated how humans interact with these systems. Our study specifically considers interaction with an agent that learns from scratch to predict the timing of an external event and communicates information about its prediction to a human user. The system learns to predict the event using a general value function, and cues the human that the event is oncoming by way of Pavlovian signaling. We study the interaction in a virtual reality environment, which simulates a frost hollow. The participant must stay in the center region in order to accumulate heat while avoiding pulses of wind, which arrive at roughly 20-second intervals. If the participant doesn't duck out of the way before the wind comes, they lose the heat they've accumulated so far. The agent's prediction of the wind is communicated to the participant by vibrating their handheld controller. Once the participant has gained enough heat to fill their heat gauge, they can raise their controller above their head to cache their heat as a unit of game reward, which cannot be lost to the wind. We test two different agents, which differ only in the way they represent time. The first uses a bit cascade representation, which discretizes time into equal chunks and resets at the falling edge of each wind event. This representation learns accurately, but requires several pulse periods for the predictions to rise above the threshold for signaling in advance of the pulse. The second agent uses a tile-coded trace representation, which discretizes time according to an exponential decay function, and also resets at the falling edge of each wind event. This representation is less accurate around the time of the hazard, but it allows the prediction to quickly rise above the threshold for signaling after only 1 or 2 periods. We conducted the pilot study with a single expert participant looking for general themes that will be worth careful investigation in a larger scale follow-up study. We found that our participant consistently tended to leave the goal region before the agent's signal when paired with the bit cascade agent, whereas they waited until after the cue when paired with the tile-coded trace agent. Qualitative notes from the participant indicate that they trusted the agent more when it learned faster, and that trust enabled the participant to modify their behavior strategically. We see the strategic behavior modification in the quantitative data as well, in events where our participant takes on unusual risks. The participant is paired with the tile-coded trace agent in 13 out of 14 instances where they race to beat the pulse by caching a point after the agent has already warned that it's coming. In conclusion, we identify trust as a major component of a person's interaction with actively learning technology, which can in turn affect strategic behavior. A larger scale follow-up study should include specific measures of trust to determine how trust is affected by online learning.
And thank you very much, Dylan, for that voiceover and that wonderful presentation. So I I like that because it shows something fundamental. We were studying in that particular example, we are studying something that may seem very far removed from neuroprostheses and neurotechnology. But I want to now, with that in mind, like, so holding that in mind, there's predictions that happen and evolve over periods of real time. And a person interacting with the technology, they may signal them based on those predictions, where that mapping, the predictions are mapped to some kind of information in a hard-coded or fixed way. I want to bring that back to the rehabilitation setting. So keeping in mind everything that Dylan presented in that particular video, and if you want a longer form version, I think Dylan has made a longer version that was submitted along with the paper to the ALA workshop. So you can go watch a longer version of Dylan giving that particular tour through the space. I want to walk back to some of the things that we've done specifically here at the University of Alberta over a span of years that actually are examples of or relate to Pavlovian signaling, to hopefully make it practical to you, and why I might say, well, yeah, of course that's straightforward. Prediction goes above threshold. You just flip a bit. This seems really straightforward. Some of the first work I want to mention is that of Adam Parker. Adam has a series of papers wherein he studied the way that we might use Pavlovian signaling in motor prediction. Imagine you're controlling a robot arm, and that robot arm is moving in some workspace. Adam's work shows that we can start to build up predictions about impacts or collisions with that workspace, and that those predictions can actually be communicated back to a person to help them change their interactions with that environment. So this is very much making a point that a machine can, in fact, in a continual learning sense, learn something by a single prediction that is useful to a human that is actually interacting with that system. One of our graduate students, Ann Edwards, did her entire master's thesis on adaptive and autonomous switching. The idea that a system like a neuroprosthesis, in this case, it was literally an upper arm prosthetic device, might be able to optimize the modes or functions in the way that a person moves through the many modes or functions of a device, whether a hand opens and closes or rotates. And one of the things that Anne found in her work was that, in fact, the mapping of predictions about what the machine was going to do to vibratory tactile stimulus that was actually delivered to a human was critical in allowing the coordination smoothing of the interactions between the person and that device. That without those kind of Pavlovian signaling interactions, a person and device got in each other's way and were unable to actually show the real performance improvements in terms of time and cognitive load in achieving the objectives of some of these manipulation tasks she was studying. Very recently, Purya Faridi, this is a graduate student in Vivian Mouchoir's lab, has been working on exoskeletal control. And we have I think, a very interesting paper in ICOR that'll be coming out later this summer, looking at using prediction learning, generalized value function prediction learning in the case of a mobile exoskeleton. And it's also switch-based control. And one thing that's come up in these conversations with Purya and the team is that, in fact, the communication, the signaling, and perhaps Pavlovian signaling of the learned predictions about user mode switching and an exoskeletal control might be very critical for that person smoothly and naturally and timely interacting with their device as they navigate through a 3D space. Walking back in the Wayback Machine, Martin Ferguson Pell and Simon Grange and Li-Ping Chi and I, back in 2013, looked at a different kind of prediction. So earlier I showed you the accumulation prediction, a prediction that rises in advance of an event. Our team looked at how we could actually predict onset of self-reported fatigue and wheelchair propulsion. How when someone's actually using their wheelchair, that we might be able to look at the residual time until they might experience self-reported fatigue, and then be able to deliver cues to that person that would change their behavior. Again, I'd like to say we have a prediction that's being learned in real time through interaction. And when that prediction crosses some threshold or via fixed mapping, that prediction is communicated to a person to help them not blow out their shoulder joints or not to exceed their ability to continue to locomote in an environment. And just stepping forward, I'm going to highlight some of the work by an intern in our DeepMind office here over the last year, Ola Kalinowska, two very nice papers that show how we might begin to take those ideas of Pavlovian signaling, again, a fixed mapping, and begin to extend into, again, this is a navigation domain, extend into a domain where an agent might be able to begin to choose when to communicate to a person and to what degree, so that you might actually start to have sparse, timely, and effective communication of those signals, be they learned predictions or observations about the world. So this is starting to place those stepping stones out of Pavlovian signaling into more fully learned or emergent communication. It's some really exciting work, and I encourage you to look it up. So that was Pavlovian signaling. And I just want to now say that there are going to be three more, I'm going to paint for you three more things I think, important capabilities or considerations that we need to start to move further across that gap between expert design signaling systems and fully emergent communication. One of them is context. I'm showing here some experiments by our PhD student, Heather Williams. She's looking on recurrent convolutional neural networks to actually allow a prosthetic system, an upper limb prosthesis, to be context aware in a sense. The idea that it might be able to know how a person is using it and where their arm is in space so that it can better provide the right control motions to a person as they are carrying out manipulation tasks. Here we have Cody Cheng from the lab, who is actually using our bypass version of this particular prosthesis to do a series of manipulation tasks. So this is one piece, context. A system being able to actually know, and I see Anna smiling over there in the audience, like context is absolutely critical for devices being able to signal at the right time and in a timely and effective fashion. I'll stop that video now, even though it's very cool, and say another piece I think we need to understand how to cross that gap, and a fundamental component is in fact a set of frameworks for thinking about how humans and how machines change as they're interacting, especially with respect to the feedback lens. One view that we've been taking lately that I think is very exciting, and hopefully we will have a paper out on this soon, is the idea that joint action is the human-human idea. The idea that two humans will coordinate their actions in time and space so as to be able to achieve joint change in the environment that they both co-inhabit. We've looked very hard at how to think about that joint action approach inside the realm of human neuroprosthetic control. And so this joint action involves a lot of modeling on the part of both agents, be able to predict what other agents are going to do, monitoring of signals, and understanding parts of a shared objective. So I think joint action is really important, and we have, again, a paper that will hopefully soon come out on that. Another is something that we thought about for a long time, and like Rich Sutton and I and Corey Matthewson and Adam Parker and a few others have worked very hard for almost a decade now thinking about what we've been calling commutative capital. The idea that we might study and think very crisply about the investment that a machine and a person make to be able to jointly act again in the future in a much more efficient way. And this may very naturally take the form of learned predictions that are learned through real-time interaction and engagement. So this is, I think, these are two frameworks I just want to call out, but I think that thinking about those co-adaptive relationships in crisp ways and trying to figure out how we might actually quantify change is critical. So with this in mind, my third piece, my third piece I think is really important is assessment. And we've made huge leaps in the last 5-6 years, especially as part of a DARPA haptics grant that many of us here at the University of Alberta were working on, led by Dr. Jacqueline Hebert. We've made huge leaps in actually assessing how someone and their prosthetic technology are interacting. We have something called gaze and movement analysis, a integrated system of motion capture and eye tracking, wherein we're actually able to monitor the joint interaction and attention of a person and their environment and their device, so we can quantify how someone moves, how they look, and where they direct their effort as they are using different forms of technology or different technological interventions. This is really exciting. I think it becomes a new gold standard for how we both assess the impact or outcomes of our choices in technology, and also, wow, yeah, Cody has managed to use the prosthetic hand to actually take off the eye tracker and nothing broken. We were all super jazzed about that. So yeah, I think this is really exciting. Those are the three pieces. I'll also say that, oh no, we can watch the final bit of the clip. That's a close big desk. I just want to give some background context as well. This isn't work that's being done here at our university specifically, but there's a lot of background effort now into developing truly high density neuroprosthetic interfaces. I'm showing a slide here from Neuralink and their flexible neural interfaces, where they literally use a sewing machine like thing to sew flexible electrodes directly into the surface of the brain. But there's also work by companies like Paradromics and others that are looking at incredibly high density recording and transmission to the central nervous system in the order of thousands or tens of thousands of possible channels of communication that can be sampled in a stable fashion in real time with very low footprints. So we're seeing transformative change in terms of actual cortical interface technology. And also this is another example, osseointegration technology. So we are doing some osseointegration surgeries here in Alberta in the Edmonton region. I want to highlight, though, this is work by Max Ortiz-Catalan, and I think it really is the gold standard and the state of the art in terms of osseointegration. The idea that you might, in fact, implant aspects of a prosthetic device directly into the bone structure of the human body, and that, in fact, you may then be also to form electrical connections by way of that implant to the muscles and nerves of the body, bidirectional communication to the nerves, to the muscles, so you might sample and record and pass through that implant directly to a mechanically affixed robotic device, electromechanical device attached to the human body. So these are two background pieces of information I want us to keep firmly in mind. Okay, water sip time. Cool. So I painted for you this gap. Now, hopefully by this time you believe me that there's good reason to cross this gap, or at least that the gap exists. And hopefully you believe me that we should consider that studying how machine learning and machine intelligence can broker the feedback relationship from a device to a person is worthwhile. Maybe just even those examples I showed you would say, you know, there's one great rehabilitation use case for those kinds of technologies. But so here I painted a picture of that simple first natural step across the pond, which I'm saying Pavlovian signaling is that step. Are there many other steps we could take? Probably, but this one is something I think that we can really understand and we can believe in as a place to build from. So as we move forward, I painted you a picture of 3 more things we might need. And this, I think, gives us line of sight to some of those other stones that might be soon rising in the water ahead of us. One of them is the context, the idea that systems might actually be able to fully leverage all of the fruitful properties of the contextual environment that surrounds the person, the device, and their interaction. Another is frameworks, that we actually start to think about how we might crisply and scientifically understand what changes in a person or a machine, or the relationship between a person and machine, as we start to change these feedback technologies and these approaches. And finally, assessment. I think we now actually have better line of sight as to what kind of gold standard assessment methods might actually let us measure those things we might want to place into our frameworks. How might we actually quantitatively, and I want to shout out to the qualitative research as well, qualitatively start to assess the way that we are actually changing a person's ability to interact with their environment through better and better machine learned feedback from a neuroprosthetic device. Finally, as well, I think we've highlighted some other things. One is that, like we saw in some of that work by Ola Kalinowska, like that we actually can start to perform a process by which a system learns when and how to signal and starts to make more informed choices driven by, say, a process of reinforcement learning. We can also start to see that, like, if model learning, and by model, I mean the ability of a system to, say, predict other aspects of its world in a reliable way and understand how that world might transition. I'm using it very generally for the computing scientists in the crowd. But frameworks like joint action, the human-human domain, really put a lot of weight on how models emerge in both parts of a human partnership, say moving a couch up the stairs and that inevitable walk-ups problem when you move into a new walk-up apartment. So I think that in fact, how we study the way that models emerge both in the person and the machine is going to be absolutely critical in fully crossing this gap. And this all points to something, I'm going to say, quite radical, something incredibly transformative, in that we have historically, and I think predominantly, thought of the interaction between a person and neuroprosthesis, either in the control or the feedback direction, as a channel coding problem to be solved. That we have to think about it as a bunch of wires and we're going to stuff bits on wires. And I want to say, this is one of the more bold things I want to say in this talk, and maybe the thing that I've come to understand over the last couple of years, is that I think we can think of it differently. I think we can, in fact, think of it as a process of 2 systems that both are able to model their world and are able to begin to cue each other to change their models. This is what Tom Scott Phillips would call ostensive inferential communication. Then, in fact, you aren't just trying to stuff bits on wires. That, in fact, one system is providing some kind of signal that is noted as a signal that will change the other system's interpretation of the world and the context. This, like, it resonates with some of those ideas from joint actions put forward by Natalie Savans and others since 2006, that we might start to think about these as 2 systems, as a partnership of systems, wherein we can alleviate a number of problems with bandwidth, with timeliness, with cognitive attention and attentional load. If we start to think about this instead as a problem of not channel coding, but of some other form of more enhanced communication, this might be transformative. So going back to our diagrams, I am speaking really now about machine learned bidirectional coordination and communication between a person and a device. And I think this gets us back to some of those things that we talked before, that a machine might in fact have something of value that it can communicate to a person that is using that machine. That in fact, that the machine might be able to make choices, informed choices, and that they could start to think about that emerging relationship as one of passing signals back and forth in a way that fruitfully enables each of them to act well in the shared environment. I want to go back to this big, sort of the big picture sci-fi William Gibson-esque slide here that I very much enjoyed making. It's one of the first new slides I've made in a very long time. And I think here that this is also part of that radical step change in thinking, is that in fact, we have thought about our assistive technologies writ large as predominantly as something that we might sort of spin up, we might train a system to use and put it in play in the world. And that system might try to, especially in terms of communication, might communicate a piece of information back to the person using the device. Person touches the wall and that force is immediately communicated back. I think we can do something even more powerful, is that we can think about that feedback pathway is in fact the system providing not just moment by moment feedback, but in fact a rich, curated, and timely predictive representation of state. That a system can actually provide forecasts of the future in a very appropriate way back to a person such that they can make informed decisions. This is one of the key lessons that came out of those frost hollow experiments of Pavlovian signaling, and something that I think was really quite a change in thinking for us as we put that forward. So we can start to move forward and actually do what Ashby said, which is we can amplify selection and choice and means in a contextual way so the system can be most used to the person using it. And this does move us from tool to partnership. It gets us back to the interaction of multiple systems and reaching again back to Ashby and Licklider and Engelbart and others, that we have a continually adapting and steadily becoming better system of interacting parts that is more in fact than the sum of those parts. So this is all very sci-fi. Hopefully I've inspired you, and now you're like, yeah, this sounds great. Tightly coupled systems. I do want to just be very pragmatic here, and this is one of the still shots from some of the work on osseointegration. This is Stephanie, one of the people who's undergone osseointegration for lower limb prosthesis use at the Glen Rose Hospital. Like, I painted you a view that was very science fiction, and so the natural next step is to say, well, that's like 10 years in the future. Like if we do anything, someone might see use of that in like 10 years in the future. And that's not the case. We have the Glen Rose Hospital here in the Edmonton region. It is a world-class rehab hospital. We have some of the best surgical interventions and best care pathways and best technologies at play. Any work that we do on improving things, like any work we do in thinking harder on Pavlovian signaling, for instance, we can actually directly put that in play to making life better for people today, not like in the long future, not even in like 2 or 5 years. Like we can start to think about how that impacts people right now, especially if we start to co-design and co-create these research approaches with the people who actually use the technology. I think that is absolutely critical. And so I just want to say one more time that we have a lot of work to do. There's a lot of topics I painted in this talk. I think that we need to do this work with enthusiasm, and we actually need to do it alongside the people who actually use the technology, the actual users of neuroprosthetic technology. So with that, I'm going to close. That was hopefully a whirlwind tour. I want to say thank you very much to everyone. There's been a ton of people involved. I have a lot of people's name on the slide, and it's in like microfilm, but it is because we've had collaborators and people interacting over a span. The ideas in this talk and the work shown over the span of more than a decade on multiple continents. We have collaborators from Europe, from Asia, from all over North America, and support from a number of really helpful funding agencies that have made this work all possible. So I want to say thank you to all these people. If your name isn't on the slide, but you did contribute, I'm sorry, but it's really hard to like go back and try to fit everything into these little things. Sometimes I miss people, but I do say thank you to everyone who's contributed to this work. And also a quick shout out before I close is that AI Week is coming up at the end of May. AI Week is putting on. If you thought this AI was cool, there's other cool AI happening here in Edmonton and around the world. There's going to be a gathering of top AI talent and some amazing minds and people, and a lot of community events later this month. So if you're interested, ai-week.ca, and you can look at how to become involved. So thank you all for your time today. I really appreciate you hearing me and giving a brand new talk, the first one I've given in many years with all new slides. Thanks so much.
That was fantastic. Thank you so much, Patrick. Okay, so we will open the floor to questions now. You can either put them in the chat or just start speaking. I will open the chat here so I can see.
Yeah, Michelle, if there's I can't pull up the chat easily right now. So if there is something in the chat, can you please read it out for me and I'll try to address it?
Yep, absolutely.
Thank you. I have a live question here from the room I'm in. Alex.
Okay, I'll start. So it's interesting to present sort of the frontier of all the research that needs to be done. But while you're talking, it sort of struck me that categorized in some ways. Sort of, this is part of where work that needs to be done. This is work that needs to be done with people. This is work that needs to be done with the implementation of software and the development of algorithms. So I was wondering if you watch out sort of maybe the totality of our efforts in time, where you're allocating or how you're thinking about that set of things, if that makes sense. Because I think that many of the things you pulled out as frontiers fit there. They all have interesting unique challenges within that subset.
Perfect, thanks. Alex, so I'm just gonna paraphrase the question if it was hard to hear on the mic. The idea is like there are a lot of things that fall into essentially the pie chart of possible areas of focus within the broader envelope I painted, and where should we start to be putting our focus, or how should we start thinking about dividing the focus? I would say, I'm going to hark back to my earlier slide, is that there is a substantial amount of work on actually, maybe some of you heard me say this, robots aren't the problem in this case. Like, we have amazing robotic technology. Actuators have come a long way. There's like soft robotics now. There's origami robots that fold themselves out and switch through holes and unfold again. So robotics are not really the problem in terms of the actuators. I see Dylan sort of being like, maybe he doesn't agree with me in the back. But there are, in fact, I think, less challenges in what I proposed in the actuator technology. Similarly, I think we've got amazing sensors. I think we have great ways to have the systems receive. There are hard computational questions. I think that's one of the areas. So not even just, do we need better algorithms? I think, do we understand the computational questions that are being asked? I think at Mars levels, like really, I think what computational questions are we tackling? I think there's huge work to be done there. And I think the actually interacting with and understanding people is the other really big bit. So putting those two things together, I think that will inform the work that we do. And we're then starting to build out a strata of case examples of how those trajectories might play out. But those for me are the two pieces that I still don't have. I haven't wrapped my mind around exactly what that looks like. So I feel like we need to put a lot of effort there, but there's lots of different touch points that we can start to think about. Cool, more questions? Michelle, anything in the chat? I have one more live one, but I want to make sure that all the other folks that are on in the interwebs have chances.
Nope, nothing on the chat yet. So go ahead, Patrick.
Okay, Anna, please.
So if one has a system or idea that is relevant to this domain context detection, how can we get involved? Is it possible to get access to data or partners and pull something up quickly?
Yeah, so the question was like, oh, well, that I'm going to paraphrase, that sounds super cool. And if we had ideas about context detection and context understanding, how might we get involved in that? Like, is there a way, like, is there data that's going to become open? And I think the answer to all of that is that, like, yes, there's now lots of touch points. I think previously, and some of you in the room, in fact, I know Anna, I'm staring directly at you, like previously, it was very hard for us to actually get the kind of data or the kind of examples and environments we needed to study, say, contextual understanding. Going back to like just that video of Cody manipulating the limb, like we now have the ability to record vast amounts of information about where people are looking, how they're moving in a task that is highly contextual, and where we can start to add additional contextual cues. We're duplicating those kind of environments in virtual reality and make them even more complex. So I feel like now is actually I think we have all the components that we didn't have 5 or 6 years ago to now be able to, especially to measure. That goes back to that assessment side. The gaze and movement analysis, I think, has been a huge step change for us, because now we can start to not just like measure how people are in context, but we can design better contexts that allow us to actually really probe the hard questions in terms of contextual assessment. So we're in a great space now. And I think that means that, yes, we will have data sets. Some of those data sets will be public. There'll be a chance to interact with experiments that are actually ongoing, and also a chance to spin up new experiments, not just in the Blink lab, but throughout the smart network. I think we're seeing a lot, like I mentioned, Puriya Friedi's work on exoskeleton control. I think we're starting to see a lot of really great environments where we can start to study context in a way we never have before. I still think that's one of the hardest things that we haven't tackled, and like the stepping stone that we need to cross to get across that gap. Context is just, it really is that. Oh, and now I've got a hard question from Craig Chapman. Uh-oh, I should duck and cover. Hi, Craig.
Hey, Patrick, awesome talk. So I have a question. You gave an example of a device that's capable of returning instantaneous feedback, like this is the force I'm experiencing right now, but also of giving predictive feedback, like the consequence of this force is that this shelf is going to tip over. How do you imagine a system is going to be able to capably deliver both of those things in a comprehensible way and not confuse them?
Yeah, so this is really cool, because I think, like, if we look at just the frost hollow experiments that Dylan narrated for us, this was a communication of a temporally extended forecast. It wasn't about the hazard, the event that was coming right now. It was about something that was going to happen in the future. And that, like, for someone in the environment, that means you're like, your controller buzzes, you're like, oh, wow, I'm getting out of Dodge. And then you do that like runaway operation and come back in. There was also another controller, the other controller that wasn't sort of noted, I don't think, but the other controller was actually giving the momentary feedback about the actual onset of the event. So you could actually, this is the cool bit about it, is you could hold up your arms and you could feel the prediction on one hand, and you could start to get a sense of that temporal interval. And it was close enough together that you could actually use like your human timing mechanism to start to build a sense of spatial association between those two cues as you were interacting with the environment. But like going beyond 2 or 3 of those, you're right, this is really hard. We had an earlier paper, it was RLDM at 2019, where we studied a similar thing. This was a fruit harvesting example, again, coming from our DeepMind office here. You can look up we have the short papers online, but it was instead using audio cues. And so we looked at Pavlovian signaling in that context. We actually looked at predictions generating audio cues, and there was different timescales involved. And just doing that in a more complicated environment, it was an audio mess. Like, it was really hard for the person engaging with the environment to make good decisions because it was not curated. And so that, like, we explored learning methods that were actually choosing when to signal and when not to signal, which had a great improvement. But I think that's where that other piece, the policy learning, like Ola Kalas's work on timely and effective communication, not over communicating, is really important. I think that, in fact, there is a role that we have to embrace the role of the machine and actually doing some of the curating of those predictions, the timescales of the predictions, and the gating of immediate versus long-term feedback, so that it is, in fact, that functional predictive representation of state. Otherwise, I think that it's going to be a really challenging process for the human to co-adapt to it. Might be possible, but it's not the naturally the smoothest or the easiest path. My 2 cents.
All right, does anybody else have any other questions? I don't see any here in the chat or any more hands up. Okay, well then I guess we will wrap this talk up. Thanks again very much, Patrick. That was really a fantastic talk.
Thank you, everyone. It was a pleasure to be here. It's nice to see all of your names and or faces remotely over the interwebs. Have a great rest of your afternoon.
Have a great weekend, guys. Thank you.